have a look at this question on your screen. You can pause the video and share your thoughts with me on the comment section. Today we're looking at the topic Unit 2 Materials for Year 12 IAL Physics. IAL means International Advanced Level Physics. And the topic is on why bones break, stress, strain, and Young modulus explained. Actually, what we're going to do in this topic is to use the idea of stress, strain, and Young modulus to explain or to understand why bones break. And this lesson is deliberately made easy so that to be a foundation to introduce you to Unit 2, which is topic material. Alright. So let's look at first the big idea in this topic. We see that all around us, we see materials in every aspect of our lives. In our homes, in the school, in every environment we find ourselves, we see different materials that are used. You see glass, you see plastics, you see wood, you see fiberglass, and also even in our bodies we have bones. A bone is a material in physics. So physics actually helps us to understand these materials and to identify their properties and be able to investigate why some materials bend under some situations, why other materials under the same situation stretch. So materials even break depending on the applied condition. And that's why in your physics, your IAF physics or IAL physics, there's one important question that the specification seeks to answer. And that is, what happens when a force acts on a material? But the whole spec on that unit is about answering this very important question. And some of you may be wondering what a material is. So I'd like to introduce myself first before I go into explaining to you what material is. I'd like to first welcome you to my channel. This channel is called Physics Intelligence Lab. And my name is Mr. Chiadi. And I'd like to take you on a journey of a fascinating study of this important topic of why bones break. So I go forward in my introduction of what materials are. In physics AL or IAL, material is actually any substance that has physical properties. By physical properties, we mean property like how strong the material is, how flexible, how stiff, or how brittle it is, and how the material also responds to different forces, it could be energy or it could be heat. And you can see on your screen there's a table below that shows you different materials and different properties they exhibit. These are some of the few materials that exist. The list of material is much, but these are the few that I would like to share with you. You can see there that the bone is also a material. And you see that the bone under the stiff column, you see that the bone is stiff, but at the same time is brittle. We're going to find out all these things as we go forward in the lesson. All right. So this lesson has a question that we seek to answer. And that question is, can physics predict a bone fracture? That's the question we seek to answer in this lesson. And for us to answer that question, we need to look at an important concept, a big idea in physics. In fact, this idea is so important that engineers, doctors, and even AI systems depend on this concept to predict failure of material or fracture of material. In fact, the three big ideas are the stress, strain, and Young modulus. We'll start with stress. And the formula for stress actually is, as you see on the screen, stress actually is not a force. It's actually, another name for stress is pressure. And stress is force spread over an area. So when we talk about a force acting on a particular area, we call it stress, or we can also call it pressure. And you can see the formula there. The symbol there represents, that symbol is called sigma, and it represents stress. Stress is actually force divided by area on which the force is applied. And you know the unit for force is Newton. The A there represents the cross-sectional area in meters squared. And the stress there, the unit is Pascal. All right. So now let me go deeper and explain to you what stress is. Let's see this diagram on your screen. You can see there are two bones there, narrow bone and a thick bone. And both of them are subjected to the same force. The same force is applied to two of them, or you can call it the same load is applied to two of them. And you see that the narrower bone experiences a higher level of stress, while the thicker bone experiences a lower level of stress. For the narrow bone, because of the high level of stress, it begins to experience fracture. While for the thicker bone, the one that has a larger cross-sectional area, you can see that the stress is low, and that's why the bone is resilient. So what does this mean? It means that if you apply the same force to a smaller area, you have a higher stress. And higher stress leads to higher chance of either failure of a material or fracture of the bone, as we can see with the bone. Like I told you, the bone is a material. See there. Now let's apply this concept to a problem. Let's see how it is applied in a problem in the next slide. The problem has been solved here. As you can see, the bone on the right of the screen, a force of 1,200 newtons were applied to a cross-sectional area on the bone of 3 times 10 raised to power minus 4 meters squared. And then you see the result there, the stress there. That's quite a high stress. That's 4 times 10 raised to power 6 Newton meter squared. The high stress, and then you can see that because of the stress, the bone was fractured. Large force applied to a small area produces high stress, which can lead to fracture or failure of material. But in this case, this is a bone and there's a failure of material. All right, so now let's share with you an important tip that will help you in your exam. Now, many students make this mistake. Now, always remember to do your conversions. Always remember. Most of the times, the cross-sectional area can be given in millimeters or even in cm. Always make sure to convert to meter square. Very important. If you're not able to convert, you're going to lose marks. Also, I'd like to point out something I'd like you to retain your memory. It's for retention. Now, bones or materials of any kind, they don't break because the force is big. Take note of this. Any material you can think of, whether glass or steel or concrete, they don't break because of the force is large or the force is big. No, they break because because the stress is high. That's why they break, not because of the force. So now let's see the second important idea that doctors and engineers consider when when they analyze bone fracture, when they analyze failure of material. And that idea is called the strain. And before we talk about this, I got to ask you a question. It says, what happens to the bone after it's subjected to a high stress or even suggested to a low stress? The bone deforms, and deformation is actually called strain. So when a material, whether bone or steel or concrete, is subjected to stress, that material deforms. And the deformation of that material is called strain. Different materials have different strains depending on the amount of stress they are subjected to. And by the way, deformation does not have a unit, and that's the formula there. That symbol there is called epsilon, and it's the change in length over the original length. So you can see from the formula that strain does not have a unit because it is a ratio of the same unit. So its change in length is in meters, and the original length is also in meters. So that's why it doesn't have a unit. All right. So let's solve a problem. This time I want you to make an attempt to solve this problem. And the numbers have been given to you there. Just try and solve it on your own. And this is this is about a bone. All right, so let's see the answer. I know you would have gotten the answer correctly if you have been following the lesson. And that is the strain of the material. The original length, you can see there, and the length increase. All right. So go to the next further idea under this unit 2. It's called the Young modulus. A Young modulus measures how stiff a material is, and in this case, how stiff a bone is. You know, when you stand up, your leg does not bend. You know, you sit down and you stand up and you move. Your body does not just fold up, and the reason is because your bone is stiff. That's why we can stand, we can walk, we can run. We don't fold up like a plastic or rubber. No, why? The reason is because our bones are stiff. Just imagine your body having only flesh and blood and there's no bone. Your body will just be flowing on the ground. And that's why bones, the skeleton, which is made up of bone, is a very important structure in human body. It's stiff, and because of the stiffness of the skeletal structure, is able to carry the weight of our body mass. All right. So your modulus actually is a measure of stiffness. It's a very important measurement in engineering and in biomedical science because it measures stiffness of a material, stiffness of bone, steel, concrete, wood, any material, and it does that by comparing stress to strain. Okay, that's why you see that Young modulus is actually comparison of stress on a material over the strain produced. Okay, so that is what is called the Young modulus. All right. So now let's look further about what Young modulus actually mean. Now, when we have a material that has a high Young modulus, I mean that material is very stiff. And that means that material also has a small deformation. So when materials are stiff, their deformation is usually small. And that means if a material is stiff, that means that material has a high Young modulus. When a material has a low Young modulus, that material can easily deform. Right. So Young modulus tells us it's a very important thing. It tells us, like I said earlier on, how stiff a material is. So high E or high Young modulus means stiff material. That means that material resists deformation. And because it can resist deformation, brittle failure risk is high. But if a material have a low Young modulus, it's going to be flexible like plastic, like rubber. And that's why those materials that have low Young modulus can stretch more easily before they break or they fail. So let's see a key insight I'd like you to have at the back of your mind. Now this applies to not only bone, but all materials we use in physics, in engineering, and in the medical sciences. All the materials we use every day, this insight applies to them. Now, two bones can experience the same stress but deform easily, and that's correct. They deform differently. And that matters a lot. So two bones, two materials, even though they are subjected to the same stress, but they can deform differently. Very important. All right, so let's see example 3. Let's see whether I can solve some problem. And here, this is a bone experience too. And this bone is subjected to a stress of 4.0 times 10 raised to the power 4 Pascal. And the strain is 0.002. So let's calculate the Young modulus. All right, so I want you to do the calculation. You can use your calculator and pause the video and do the calculation. All right, so see the answer here. You can see this is a high Young modulus. That means the material definitely will be stiff material. You can see from the question the deformation is quite small compared to the stress. All right, so as we come to the end of the lesson, I'd like to look at the fracture model. right? This model applies not only to bones but other materials. Now, see that when a force is applied, you can get force on an area, you get a stress, and then the bone deforms, you have a strain, and then the strain, the stress and the strain give us the Young modulus, which is the stiffness of the material. And if the limit of that material is exceeded, as you can see in the bone, a fracture occurs. I'd like to point out that in the starter that I shared with you at the beginning of the lesson, I know many of you would have thought that what made the, the second player to break his leg was because too much force was applied. So that is incomplete. So it wasn't that too much force was applied, but because of the stress that the bone was subjected to. Alright, so don't say it's force, say it's stress that the bone was subjected to. And that was what led to the bone of one of the players and on the starter I shared with you at the beginning of the lesson to break. And you see there today in this lesson we are able to answer the question that at the start of the lesson. If you remember, the question we sought to answer from this lesson. Can anybody remind me the question? The question was, can physics predict a bone fracture? So you can see from all we have done, the explanation and the problems we're able to solve, that bone fracture or material failure is not random. It is a predictable physics failure. It is a predictable physics fracture. So bone fracture physics can be used to predict bone fracture or material failure. All right. So our lesson question has been answered from all we have done through this lesson. So as we round up the lesson, I'd like to point out some misconceptions that many students have about this topic. Number one, many students use diameter instead of the cross-sectional area when they are calculating stress. Stress is force over cross-sectional area, not force over diameter. So take note of that. Another misconception is that students forget to convert millimeter square to meter square. The units there must be conversion because we use SI units. Then students also give unit for strain. That's wrong. Strain does not have a unit. And at times, students also mix up stress and Young modulus or Young modulus. They mix it up, okay, because they have the same unit. So, but they are different things. Young modulus is a measure of stiffness of a material, so it's not the same as stress. So don't mix up the two of them. All right, finally, let's answer this question on Isaac ticket. I want you to quickly send me your answers on the chat box. The doctor says this patient bone has a low Young modulus. Explain what this means. I'll pause the video and type in your answer. But I know that your answer should be close to this. And it's very simple. The bone is less stiff, so it deforms more easily when a force is applied. So we've come to the end of this lesson. I look forward to see you in the next video And in the next lesson, we're going to talk about sports injuries. And we're going to see how we can use physics to prevent sports injuries. See you in the next video. Bye bye.